In this video, we're going to focus on how to do some important calculations regarding calorimetry. We'll begin by reviewing some of the basics of calorimetry, as well as working through some of the more challenging examples to help you get a feel for what kind of questions you might see. So let's start with some basic calorimetry in problem number 1. It takes 213 joules of energy to raise the temperature of 110.1 grams of nickel from 23.61 degrees Celsius to 27.19 degrees Celsius, and we're asked to calculate the specific heat capacity and the molar heat capacity of nickel. So when we have a basic calorimetry problem like this one, we can use the equation Q equals MCAT, where Q is the energy, M is the mass of the sample, C is the specific heat, which is what we're trying to find in this problem, and delta T is your final temperature minus your initial temperature. So in this problem, our final temperature would be 27.19 degrees Celsius, and our initial temperature is 23.61 degrees Celsius. So once you have all the numbers, all you have to do to solve for the specific heat capacity is plug them all in. So for Q, we have 213 joules equals M, which is 110.1 grams, C, which is what we're trying to find, and our delta T, which is our final temperature minus our initial temperature. So now that we have one equation and just one variable, we can manipulate the equation to solve for C. So right now we can just say C is equal to 213 joules divided by 110.1 grams times delta T, which is 27.19 minus 23.61, and that is 3.58 degrees Celsius. So now this is our final equation, and you can just solve this by plugging it into your calculator, and you should get that nickel has a specific heat of 0.54, remembering the units, joules over grams degrees Celsius. So now we know our specific heat capacity of nickel to be 0.54 joules over grams degrees Celsius. But we're not quite done yet. We still have to find the molar heat capacity of nickel. And to do this, we can still use the same equation, Q equals MCAT. Because we know our delta T, we know our M, and we know our C. So just some clarification on what exactly molar heat capacity is. It's the amount of energy necessary to raise 1 mole of a substance 1 degrees Celsius, or 1 degree Kelvin. So because we're trying to find the amount of energy necessary to raise 1 mole of nickel by 1 degrees Celsius, we know our delta T is just 1. And we also know our C from our last problem, which is 0.54 joules over grams degrees Celsius. And we know our M because we know that the molar mass of nickel is 58.69. And you can just get this from a periodic table. So now that we have M, C, and delta T, we can solve for Q, which is the amount of energy that's needed. And we can just multiply 1 by 0.54 by 58.69 to get final answer of 31.71 joules. And so the molar heat capacity of nickel is 31.71 joules. Now let's try a slightly more challenging problem. A 31.1 gram sample of water at 270 degrees Kelvin is mixed with a 53.3 gram sample of water at 310 degrees Kelvin. Calculate the final temperature of the mixture, assuming no heat loss to the surroundings. So we have two samples of water at different temperatures and with different masses, and they both arrive at the same final temperature. So this illustrates a very important concept in chemistry, and that's called thermal equilibrium. Thermal equilibrium is the idea that when you mix two substances of different temperatures together, they'll eventually reach the same temperature. So that's why the final temperatures of these two samples are the same. Okay, so we can start solving this problem using the same approach or a similar approach that we used in the last problem, and that is just starting with Q equals MCAT for both the samples of water. What's interesting about this problem is that because the final temperatures are the same, because the final temperatures of the two water samples are the same, the amount of energy lost by the hotter sample is equal to the amount of energy gained by the cooler sample. So the amount of energy, or Q, lost by the sample at 310 Kelvin is equal to the amount of energy gained by the colder sample, which is the sample at 270 Kelvin. In other words, Q of the 270 Kelvin sample equals negative Q of the 310 Kelvin sample. And we can actually rewrite this as MCAT equals negative MCAT. Okay, so now that we have an equation, we just need to plug in all the numbers. The M for the 270 Kelvin sample is 31.1 grams. The C for any sample of water is always 4.18 joules over grams degrees Celsius. And the change in temperature is our final temperature, which is what we're trying to find, minus our initial temperature, which is 270 Kelvin. And this is equal to negative MCAT, which is negative 53.3 grams times 4.18 times the final temperature we're trying to find minus 310 Kelvin. So now all that's left to do is simplify all of this math. So we can start by multiplying the masses by the specific heats on both sides. On this side, we have to do 31.1 times 4.18, and that is 129.998 times our final temperature minus 270 Kelvin. And on our left-hand side, we have to solve for 53.3 grams times 4.18, which is 222.794 times our final temperature minus 310 Kelvin. So simplifying this even more gives us 129.998 final temperature minus 270 Kelvin times 129.998, which is 35,099.46. And on our left-hand side, we have negative 222.794 TF plus, because there's two minus signs, 310 times 222.794. And that gives us positive 69,066.14. So now all that's left to do is combine like terms. So we're going to bring all the final temperatures to this side. So we can do that by adding 222.794 to 129.998. And that is 352.792 TF equals, and now we have to combine like terms on the other side of the equation. And we can do this by adding 69,066.14 and 35,099.46. And that gives us 104,165.6 Kelvin. And now we just divide both sides of the equation by the coefficient to TF because we want to get TF alone. So dividing 104,165.6 by 352.792 gives us a final temperature of 295.26 Kelvin, or just 295 Kelvin. And that's our final answer. Now let's try a slightly different problem. Still very similar to our last one, but this time we are dropping a hot metal into water. And this is actually a really common example that you'll see in calorimetry. The question is, determine the final temperature when 10.0 grams of aluminum at 130 degrees Celsius mixes with 200 grams of water at 25 degrees Celsius. And we know that the specific heat capacity of aluminum is 0.901 joules per grams degree Celsius. So we can start this problem the same way we looked at the last one. We know that since both the aluminum and the water arrive at the same final temperature, both of them would have had the same amount of energy transformed. So in this case, the hotter substance is the aluminum and the colder substance is the water. So we can say that Q aluminum equals negative Q water. Because Q equals MCAT, we can say that MCAT of the aluminum equals negative MCAT of the water. So now that we have the equation, all we gotta do is plug everything in. The mass of aluminum is 10.0 grams. Its specific heat is given up here, it's 0.901. And the final temperature is unknown, but the initial temperature is 130 degrees Celsius, and that equals negative MCAT of the water. The mass of the water is 200 grams. The specific heat is always 4.18, and the final temperature, again, is unknown, but the initial temperature is 25 degrees Celsius. Perfect. So now we have one equation and only one variable. So all we have to do is simplify this out. And it's pretty self-explanatory, so I'm just going to get started. So by simplifying this equation above, we have a final temperature of 26.12 degrees Celsius for both the aluminum and the water. Now let's try a problem that's a little bit different. In a coffee cup calorimeter, 1.67 grams of NH4NO3 is mixed with 74 grams of water at an initial temperature of 25.03 Celsius. After dissolution of the salt, the final temperature of the calorimeter contents is 23.17 degrees Celsius. Assuming the solution has a heat capacity of 4.18 joules over grams degrees Celsius, and assuming no heat loss to the calorimeter, calculate the enthalpy change for the dissolution of NH4NO3 in units of kilojoules per mole. So this is a coffee cup calorimeter problem. And basically what a coffee cup calorimeter is, it's an enclosed coffee cup with a thermometer, some water, and a reaction. In this case, it's NH4NO3, which is reacting. So for these kind of problems, we use another formula that goes like this. Q system equals Q water, or Q solution plus Q reaction plus Q calorimeter. So in other words, the total net energy of the system is equal to the energy change of the solution plus the energy change of the reaction plus the energy change to the calorimeter. But in this problem, since we are assuming no heat loss to the calorimeter, we can just rule that one out. And because we assume that generally no heat enters or escapes the calorimeter, we can say that Q sys equals 0. And this leaves us with Q solution plus Q reaction equals 0. And from this, we can see that Q solution equals negative Q reaction. So to find the heat of reaction of the NH4NO3 dissolving in the liquid, we can basically just take the negative of our Q solution value, which we can calculate using the values we have for water and NH4NO3. So let's get started with this problem. We're trying to find Q reaction, or the enthalpy change for the dissolution of NH4NO3. So, since we don't really know that much about the heat of reaction, we can start with our Q solution. And our Q solution, as always, is equal to MCAT. So in this case, our mass is 74.0 grams from the water, plus the 1.67 grams from the solute. Our C, we can just assume that's 4.18 joules over grams degrees Celsius, because that's what we were given in the problem. And for our change in temperature, we have 23.17 as our final temperature and 25.03 as our initial temperature. So 23.17 degrees Celsius minus 25.03 degrees Celsius. And now all we have to do is calculate that, and what we get is 74 plus 1.67, which is 75.67 times 4.18 times this, which is negative 1.86. And this simplifies to negative 588.32 joules. So that's our Q solution. And we know that our Q solution is our negative Q reaction. So we can just say that our Q reaction is equal to 588 0.32 joules, or 0.588 kilojoules. But we haven't solved the problem yet. We still need to find the enthalpy change in units of kilojoules per mole. So we have it in kilojoules, but we gotta remember that this is only for 1.67 grams of NH4NO3. So we need to find this for 1 mole of NH4NO3. So in other words, we need to convert 1.67 grams of NH4NO3 to moles. So the first thing to do here is to find the molar mass of NH4NO3. You can calculate the molar mass of NH4NO3 by adding up the molar masses of 2 nitrogens, 4 hydrogens, and 3 oxygens. And if you did that, the molar mass there would be 80.043 grams. So now that we have the molar mass of NH4NO3, we can convert 1.67 grams of NH4NO3 to moles. And how we do this basically is just divide the amount of grams of NH4NO3 by its molar mass. And when we do this, we see that we have 0.021 moles of NH4NO3. So now we just need to divide our original energy value, 0.588 kilojoules, divided by 0.021 moles. And we have a final value of around 28 kilojoules per mole. And that is our enthalpy change for the dissolution of NH4NO3. So that is our Q reaction in units of kilojoules per mole. Now let's try our last example, a bomb calorimeter problem. So the energy content of food is typically determined using a bomb calorimeter. Consider the combustion of a 0.47 gram sample of butter in a bomb calorimeter having a heat capacity of 2.67 kilojoules per degree Celsius. If the temperature of the calorimeter increases from 23.5 degrees to 29.1 degrees, calculate the energy of combustion per gram of butter. Okay, so before we begin this problem, let's familiarize ourselves with what a bomb calorimeter is. So unlike a coffee cup calorimeter, it is not a constant pressure calorimeter. It's actually a constant volume calorimeter. So you have a box similar to this one. It's filled with water, usually has a thermometer in it, and it has a combustion chamber. And in this combustion chamber, that is where the reaction occurs. So you usually have like a solute or some sort of substance in there. And when it combusts, it releases energy into the water. And we can measure the change in temperature of the water to measure the energy change. Okay, so let's get started with our formulas. So similar to a coffee cup calorimeter, we use a Q-sys equation for bomb calorimeters as well. Except this time we have Q-sys equals to Q bomb, and this little chamber is called a bomb, by the way, plus Q reaction, plus Q water. So in other words, the energy gained by the water, the energy released by the reaction, and the energy of the bomb is equal to our energy of the system. And our energy of the system is usually equal to 0, so we just assume it equals 0. So in most cases, we can just say that Q reaction equals negative Q bomb plus Q water. And also notice that our bomb calorimeter is said to have a heat capacity of 2.67 kilojoules per degree Celsius. This is given to us in the problem because we need it to figure out our Q bomb. The equation for Q bomb is always C bomb times the change in temperature. So let's go about calculating this first. Our Q bomb is C bomb times the change in So let's get about calculating this first. Our Q bomb is equal to our C bomb times the change in temperature. So we can say for this problem, our C bomb is 2.67 kilojoules over degree Celsius. Our change in temperature is 29.1 minus 23.5 degrees Celsius. So simplifying this out, we get 2.67 times 5.6. And this equals about 14.95 kilojoules. So now we have the total amount of energy generated by that combustion. But we got to remember that this is just for 0.47 grams. We need to calculate it for 1 gram, so what we just need to do is divide our energy value by the amount of grams we have to get the energy per unit value. And that is 14.95 divided by 0.47, which is equal to about 31.8 kilojoules. And that is our energy of combustion per gram of butter.